Okay. Okay, good. So today we are going to talk about the RSA cryptosystem, about Fermat's little theorem, which is what makes the RSA cryptosystem tick. And then if there's time left over, then we'll do a little bit of a review of modular arithmetic. Okay? Okay? All right, so let's back up to where we were last time. So okay, last time we talked about what it meant for a function to be one-to-one, onto, and a bijection. A bijection is one-to-one, onto, right? A bijection, here's a way to think of a bijection. A bijection is just a renaming of all the elements of a set, right? That's what it is. So, for example, one bijection that we would have if you're working mod 15 is f of x equal to 4 times x mod 15. No? Bijection, not a bijection. No? Should we try it? Let's see. 0 maps to 0. 1 maps to 4. 2 maps to 8. 3 maps to 12. 4 maps to 1. 5 maps to 5 fours are 5. So far, so good, right? 6 maps to 9. 7 maps to 13. Should we switch colors? 8 maps to 2. 9 maps to 6, right? 10 maps to 10, 11 maps to 14. So far, so good. What do you think? Is it a bijection? It's a bijection, right? So there are 3 unfilled spots. Let's just fill them in. It must be like this, right? It must go, if it's a bijection, that's what it's got to be, and we believe it's a bijection at this point. Okay, so just check that it is. Okay, so this was a bijection. Let's do another one. F of x equal to x squared mod 15. I think we tried it last time, but let's do it again, just to make sure we're on the same page. So x squared mod 15, we don't expect that to be a bijection, right? We don't, because x and minus x have the same square, right? So, but still, let's do it. So 0 goes to 0, 1 goes to 1, 2 goes to 4, 3 goes to 9. Oops, 3 goes to 9. 3 goes to 9. 4 goes to 1. 4 goes to 1. Okay, let's. Okay, 4 goes to 1. Okay, that's already a surprise, right? Because 1 and 4, 4 is not the same as minus 1, right? So that's a bit of surprise. How about 5? 5 goes to 10, right? 5 5s are 25, that's 10 mod 15. 6 goes to, 6 squared is 36, is 6. So 6 goes to 6. 7 goes to 4. Okay, that's another surprise, right? Because 2 and 7, this is not minus of that. In fact, if you want to now know what about the rest of them, we can just say, well, everything below the line is just minus of what's above the line. Right? So 8 is the same as minus 7, 9 is the same as minus 6. Right? So we can just copy those over. So we know that 8 squared is the same as 7 squared, minus 7 squared. Right? Minus 7. Okay, so 8 squared should be the same as 7 squared, so this should also give us 4. So now 4 has at least 3 square roots. Right? Over the, if these were integers or real numbers, we'd say they should have at most 2 square roots, right? Plus and minus. Now we have at least 3 here. Okay, what about 9? 9 is the same as minus 6. So 9 squared is the same as 6 squared. 10 is the same as minus 5. So 10 squared is the same as 5 squared. 11 is 4. So 11 squared is 1. Okay, so 1 has now at least 3 square roots. Right? 12, same as 3. So 12 squared is 9, right? 13 is the same as 2. So look, I mean, it just doesn't stop, right? 4 has 4 square roots. And 14 is the same as 1. 14 is the same as 1, right? So 14 squared is the same as 1 squared. So 1 also has 4 square roots. Oops. Right? Okay, so definitely not 1-to-1, definitely not onto, right? But it's sort of interesting. Now, actually, the fact that 1 has 4 square roots is actually quite significant. And you'll learn about this when you do 170. Okay? Actually, okay, here's the case. How many of you have heard about quantum algorithms? How many of you have heard about quantum computers? How many of you know that quantum computers can factor numbers very quickly? Okay, that's based on this. Okay, that's based on this fact that if you're working mod numbers like 15, 15 is a number that you can factor, it's not a prime. Well, then 1 has more square roots than you expect. The fact that it has more square roots than you expect is what, this is the toe hole that quantum computers get, and they exploit it to the fullest. Okay, that's what they do. Okay, okay. So now, let's try to do. Yes, sorry. I'm sorry. Okay, so why does 1 have more than? Okay, so. You want to know what's going on behind the scenes, or you just want to know what the calculations look like? Or you want to know what happens behind the scenes? Okay, so let me just tell you. Okay, so how about an aside? I'll tell you what's going on behind the scenes, and as long as the only thing, the only condition, the one condition under which I should do this is that those of you who aren't going to follow it, just don't listen to what I'm going to say next. Okay, okay, sorry, that comes off sounding funny, but okay, so if you get confused at any point, you can stop listening and just think about something else. Okay? Okay, so here's what's going on behind the scenes. See, when you work modulo, so if you're working mod 15, here's another way you can work mod 15. The factors of 15 are 3 and 5. Okay? So to keep track of a number mod 15, you can keep track of what it is mod 3, and you can keep track of what it is mod 5. Once you know what it's mod 3 and 5, you know what it is mod 15. So this is something that the ancient Chinese knew. So it's called the Chinese remainder theorem. Okay? Okay, so this is this is another way of counting mod 15. If you don't have the resources to count mod 15, just hire 2 people, one of whom can count up to 3, one of whom can count up to 5, and just that's good enough. Then you can count up to 15. So now let's look at how many square roots are there of 1 mod 3? Well, there's plus and minus 1. Okay, so mod 3, there are 2 square roots, plus and minus 1. What's plus 1? Well, that's 1. What's minus 1? It's 2, right? So this is equal to 1 and 2. Right? Those are the square roots of 1 mod 3. What are the square roots of 1 mod 5? Plus and minus 1. Right? So plus and minus 1. What's plus and minus 1 mod 5? 1 and 4. Okay, now, what happens if you square this number? So suppose you have a number which is plus 1 mod 3 and plus 1 mod 5, and you square it. What happens to it? Well, you square the number mod 3 and you square it mod 5. So what you get? 1 and 1. So what's the number which gives you a remainder of 1 when you look at it mod 3 and 1 mod 5? That's 1. Okay, so if it's 1 mod 3, 1 mod 5, what does it look like mod 15? Also 1. How about if it's minus 1 mod 3, minus 1 mod 5? What does it look like mod 15? Also minus 1. So that's minus 1, which is 14. 14 is that number where it gives you a remainder of 2 when you divide it by 3 and 4 when you divide it by 5. Right? Because it's minus 1 in each case. But now there are these other square roots. What if you want a number which gives you a remainder 1 when you divide by 3 and minus 1 when you divide by 5? This is one of these other numbers. It's another square root of 1 mod 15. Because when you square it mod 3, you get 1, square it mod 5, you get 1. What do you get when you square this number? You get 1 mod 15, right? But what is this number mod 15? It's 1 mod 3 and minus 1 mod 5. How do you get that? Right, so 1 mod 3 minus 1 mod 5. 4? Is it 4? Right, because 4 is 1 mod 3 and it's minus 1 mod 5, right? So that's another square root of 1 mod 15. Right, so when you square 4, you get 16, which is 1 mod 15. But the reason you do what's going on behind the scenes is this is what's going on behind the scenes. Similarly, if you look at minus 1 and 1, what's 1 mod 3 and minus 1 mod 3 and 1 mod 5? Probably 11, right? So that's your other square root of 1 mod 15. So somehow, okay, so what's happening here? Well, 1 and minus 1, behind the scenes, what's happening is what you expect. But these other two, what's happening behind the scenes is it distinguishes between 3 and 5, the two factors of 15. So now if you can find such a square root, you've distinguished the two factors, and you can actually factor the number quickly. Okay, and this is what the quantum algorithm does. It finds such a square root, and now now it's got a handle on what's going on behind the scenes, and then it factors. Okay? Is that what you were looking for? That's probably much more than what you were looking for. Yeah. Sorry, can you say that again? how does it become 11? Well, okay, so, this is, if you want to know what's the procedure to do this, there's actually a procedure to do this called Chinese remaindering. But if you look at what's, minus 1 mod 3, well, that's got to be either minus 1 or 2 or 5 or 8 or 11 or 14, right? What about 1 mod 5? It has got to be either 1 or 6 or 11, right? And so which one is common between the two? It was 11, so that's what it is. So you want to satisfy both these conditions, and that was the only way to satisfy both. Okay? Yes?
You know how you said plus or minus 1 is the square root of 1?
Yeah.
So why wouldn't like 4 work? Like 5?
Why wouldn't?
Why wouldn't 4 be the square root of 1?
Mod 5? In fact, it is. So I said the square root of 5 is, of 1 mod 5 is plus and minus 1. But what's minus 1? Minus 1 is the same thing as 4. So that's why I said the square roots are 1 and 4. Yeah? Okay. Yeah? Okay, so now let's try to look at another way of, so squaring was not a bijection mod 15. So let's see something else which is a bijection mod 15. Okay? And it sort of looks like squaring, but it's a bit surprising that it's not it ends up being a bijection. And the fact that it's a bijection is, this is what's behind this is the main sort of fact that goes into making up this RSA crypto system. Okay? So we look at f of x equal to x cubed mod 15. Okay? Looks a little bit like taking squares mod 15, but the properties are very different. So let's try it. So 0 gets mapped to 0. 1 goes to 1. Okay, so far this was easy, and now I hope you're going to help me with the rest. Okay, so 2 goes to 2 cubed is 8. Right, so now what's 3 times 3 times 3? 27, which is 12. 27 is minus 3, which is 12, right? Okay, so 12. Let's see. 27. Okay, 4 times 4 times 4. Okay, 4 times 4 is 1, right? See, we are working mod 15. So 4 times 4 is 1. 1 times 4 is 4. So 4 cubed is 4. Okay, what's 5 times 5? 10, right? 5 times 5 is 10. Okay. Yes? Does everyone agree? 5 times 5 is 10? And 10 times 5 is 5. Right, good. Okay, so 6 times 6 is 6. And 6 times 6 is? Okay, good, 6. Okay. 7 times 7 is 4. And 7 times 4 is? 7 times 4 is minus 2, right? 13. 13, okay. 7 times 2 is 4. Okay. Okay, what about the rest? What should we do for the rest? Negatives. Oh, good. See, because from here on, if we have x up here, then we have minus x down here. So when you take minus x cubed, you get minus x whole cubed is minus of x cubed. So you'll just look up the thing up above and then take minus of that. Right? So, okay, so let's fill that in. So 8 cubed is the same as minus 13, right? Minus 13 is 2. Okay, what's 9 cubed? It's minus 6, which is 9. Good. 10 cubed minus 5, which is 10. 11 cubed minus 4, which is 11. 12 cubed. So it's minus 12, which is 3, right? Does everyone see what I'm doing? So for 12 cubed, you look at what's minus 12, which is 3. You see where 3 maps to, it's 12, so you go to minus of 12, which is back to 3. 13 cubed, so you look up what 2 gets mapped to. 2 gets mapped to 8, so you go to minus 8, which is 7. And 14 gets mapped to 14. Good, so it's a bijection. Okay? Okay. Now, what's a bijection good for? See, a bijection is a scramble. It's a renaming of your objects, right? So if you're mapping from the numbers mod 15 to the numbers mod 15, right? Well, you're renaming the numbers. That's a way of scrambling things up. Okay, that's why it comes up in encryption. It's just a way of renaming. Think of the numbers on the left as your messages. Then you're scrambling them up and sending an encrypted message. Right? That's what this is doing for you. Okay, now here's another. Okay, so here's what's going on behind the scenes in this encryption function. So remember what we have here is 15 is 3 times 5. Right? It's a product of 2 primes, P and Q. 15, 3 and 5. Okay. Now, what did we do? How did we pick, why did we pick x cubed mod n? So we picked this encryption, which was, so we picked, this was n equal to 15. E we picked equal to 3. Right? So we picked some number such that GCD of 3, so this was E, and 2 times 4 is 1. Where did I get 2 times 4 from? It was 3 minus 1 times 5 minus 1. P minus 1 times Q minus 1. Okay? So I'm just showing you what the recipe was. How did we get there? Right? So we picked such a number E, and we said, our RSA function is going to be, if we start with x, we'll raise x to the E mod n. So E was 3, we take x cubed mod n. Okay. Now, what do we know when we say GCD of 3 and 8 is 1? Well, what it tells us from what we did last time is that 3 has a multiplicative inverse mod 8. We can write down 1 over 3 mod 8. Okay, so what is 3 inverse mod 8? Which number do you multiply by 3 to get 1 mod 8? 3, okay. Okay, so this was an unfortunate fact, but I didn't want to deal with numbers which are larger than 15 here, so we have to live with it for this example. Okay, so now, but still, it's not so bad, because what we are claiming is, if you call this number D, then if you end up with a number Y here, and you want to know what gets mapped to Y, you just take Y raised to the power of D mod n, and you get the inverse. Okay, so So what we were saying was there's a bijection, right? So every element, if you want to know where it maps to, it maps to something on this side. And how does it map? You take this number and you cube it, and you get to the number on this side. Now if you want to go back, one way to do it is you just search through everything and you see which one mapped there. That's a very inefficient way of doing it. What this is telling us is that there's a shortcut. What you do is you compute this decryption exponent. You compute this D, and you look at the number that you've ended up at, and you want to know what mapped to it. Well, you take this number, you raise it to the D. Well, D happens to be 3 in this case, so you take this number and you cube it, mod 15, and you know where you came from. Okay? So it's very slick. So this is the beautiful thing that RSA discovered about 35 years ago. Okay? So let's try it. We've already done this. Now let's compute d of y equal to y to the little d mod n. Okay, so let's see what happens if we do that. So what do we want to do? Well, we want to see. So if you take 0 and you cube it, what do you get? You get 0. Oh, is that a good? If you take 1 and you cube it, you get 1. Anyone like these colors? Maybe. Let's try this one. If you take 2 and you cube it, you get 8. See, it goes back to where 3 and you cube it. 3 3s are 9, 3s are 27 is 12. So you go back down here. 4 and you cube it. Yeah, 4 squared is 1. 4 times 1 is 4. So you can check. If you cube these, you go back to where you came from. Okay? In fact, you can see it in this. So let me just erase these new lines here and show you something. Okay, so if you look at these lines, they either go straight across, which means that when you go back, you get back the same thing, or they go in pairs, right? If 13 goes to 7, then from here 13 goes to 7, right? So they exactly cross each other, which means if you go from here, right, you come back that way as well, right? It's exactly, so that has to do with the fact that the decryption exponent was also 3. Okay? Yes?
So this only works if the thing in modding y has 2 prime factors?
Yeah, it has to have 2 prime factors here for this to work.
And only
So,
2 prime factors?
I'm sorry?
And only 2 prime factors?
Yes, so, well, you can generalize this, but it turns out that what this relies on, what this is going to rely on, okay, we are getting ahead of the story, but it's, all this is going to rely, the security of this scheme is going to rely on the fact that factoring is hard. Right, remember we talked about this, that factoring numbers is a really hard problem. Our best algorithms take exponential time. Now, some numbers are easy to factor. The numbers that are easy to factor are those which have small prime factors, because you can just read them off. You can just try trial divisions. So the way you make sure that your number has only large prime factors is you make sure there are few of them. Okay, so how do you make sure your prime factors are as large as possible? Well, what you would do is make sure there are as few prime factors as possible. Well, what is the fewest prime factors you could have? 1, right? But that's silly. That's not hard. So if I give you it turns out it's easy to tell whether a number is a prime. Okay, that's something you'll see in 170. Okay, so that's another thing that goes into the RSA cryptosystem, the fact that we can tell when numbers are prime. But now, what's the next hardest case? You know, what are the next biggest prime factors you can have? Is when there are exactly 2 prime factors, and both of them are approximately equal in size. So in RSA, you pick maybe a, you know, if you're trying to be very secure, you take a 1,000-digit number, which is a product of 2 500-digit numbers. Right? So P and Q, which are each 500 digits long, you multiply them together, you get N, which is 1,000 digits long. And now you challenge anybody to factor it and say, you know, right? So if you were to pick 2 500-digit numbers, and there are efficient ways of doing this, you multiply them together, then there's a secret that you know that nobody else can possibly guess without factoring that number, right? Okay, so that's sort of an unprecedented level of security, right? So you can be pretty certain that nobody is ever going to guess your secret, well, at least until a quantum computer is built. Yes?
So when you're picking E, can you pick either of the factors, or is there a convention?
Oh, no. Sorry. Okay, sorry. This was an unfortunate accident that E turned out to be one of the factors. Okay, but that's not how we picked E. Okay, what did we do to pick E? We just picked any number which is relatively prime to P minus 1 times Q minus 1. Okay? And now, usually in RSA, you try to pick E equal to 3. Why would you want to pick E equal to 3? I'm sorry? Yeah, it's so that encryption is quick. So you know, imagine what would happen if when we did this exercise. Suppose I had picked E equal to 7. Yeah. We'd have been working a lot harder. But now imagine that N was a 1,000-digit number, right? And we picked E to be a 900-digit number. Right? That would take a lot of multiplications for us to compute x to the E. Right? So that's why you try to pick E equal to 3, so that it's very quick to compute x to the x cubed mod n. Yes? Yes, they are. Yeah, everybody has, so in RSA, everybody has their private P and Q, which they don't reveal to anybody else. That's their secret information. And then they publish N, which is P times Q. Right, so they put up N on their web page. Maybe they put up also N and E. Right, if you know, E might be by default 3, or if they want to choose something else, they choose it, and their public key is N and E. Right? But they keep P and Q secret, and of course D secret. Yes. Yes.
So the P and Q, who knows the P and Q, like the sender of the message and the
No. P and Q are secret. So you know, you pick your key. So you pick P and Q. Right? Multiply them together. You figure out what E should be. Hopefully it's 3. Now on your web page you publish N and E. Right? Meanwhile, you also calculate what D should be. Right? You calculate D by saying, you know, you compute P minus 1 times Q minus 1. You can do it because you know P and Q. And then you compute E inverse mod P minus 1 times Q minus 1. So this is your secret decryption exponent. At this point, if you want, you can throw away P and Q. Right? You shred it. Nobody ever finds out what P and Q is. You also keep D secret. Right? Don't even tell your best friend. Okay? Okay, so now that's the setup. Everybody knows N and E. Only you know D. Yes?
A large number is E. Don't we have the same trouble E taking a really long time?
How long is little d?
Yeah.
Yeah, that's the problem. You know, so So D is going to be roughly as large as n. Right? So if n is 1,000 digits long, D is going to be 1,000 digits long. And so computing y to the d mod n is going to be pretty hard. You know, if you just try it, you'll keep doing it. Actually, you wouldn't do anything else for all your life, or for the life of all your descendants, or for the life of all you know, for the life of the universe, right? So it would be much longer than anything you could ever imagine, unless you take a course on algorithms, maybe CS170, and then you'll learn how to do it very quickly. Okay, not as quickly as computing x cubed, but still pretty quickly. Okay, and that's the secret. That's another of the secret sources in RSA, is how do you compute this y to the d quickly? That's a very good question. Yeah? Okay. Yes?
Let's suppose that you have P and Q at 4 and 5,
Yeah.
and then just P minus 1 and Q minus 1 will be 3 and 4, right? And then 3 times 3 and so
Yeah, good question. So question was, well, what if, well, first of all, P couldn't be 4, but, right, but let's say it was something else. So suppose P minus 1 was divisible by 3. So suppose P was 7, right? So P minus 1 is divisible by 3. So now you can't use 3 as your encryption exponent. So what do you do? Well, there are two possibilities. Either you pick some other encryption exponent, maybe 4, 5, 6, something else, or don't pick 7 as your prime factor, right? So usually what you do is you generate a prime, and then you make sure that your prime is not congruent to 1 mod 3. So when you subtract 1 from it, it's not a multiple of 3. Yeah.
So would that factor just infinite n, or can n be any number with any number of prime factors?
No, n is always going to be a product of two large primes. Right? Okay. Yes?
could E and Q be the same prime?
That would be very an unfortunate choice, because then it's easy to factor that. Yeah? Yeah. Okay. So how do you feel on stamina? Do you want to keep going? Do you want to take a break? Break? Yeah, let's take a break. Yeah, sorry.
Question here, I'm not sure exactly what it means. For every n greater than 1 stable marriage instance, with n man and n woman to unstable pairing, and with every unmatched man woman pairing to a couple, I thought we already proved that any stable marriage instance with the same number of men and women have a solution.
Yeah, but we are saying that there's a, sorry, instance meaning there's a, you know, there's a set of men and a set of, the instance doesn't mean a stable marriage. It means a problem. It's a problem like this, such that there's an unstable pairing. So we know there's a stable pairing, but show that there's some unstable pairing. You know, it's unstable, meaning you paired up some people, but now you paired them up, and now you want to show that it's so unstable that everybody you haven't paired up,
Wait, everybody
who hasn't been paired up, is a rogue couple.
so there's some sort of incompleteness.
It's sort of saying, you know, this happens to be the most unfortunate pairing possible.
So
Where-
essentially, once when you have a man-woman pairing, so each person in this pairing is part of a rope.
Meaning, maybe let me explain this. You know, since you're having trouble with it, maybe I'll explain it to the class right afterwards. So it's It's the second problem, right?
Yeah, second problem.
Okay, I'll just explain it right now. Yeah, yeah. Hi.
So you said it was fairly easy to check whether a number was prime.
Yeah.
So why can't you check whether a number is prime and then also check whether n is divisible by that number? Wouldn't that make factoring easier as well?
Because you don't know what the primes are. You know, there are lots of primes.
Right.
And so you'd have to try all of them if you try that.
Okay.
So you're looking for a needle in a haystack. That's the problem. Okay. Okay, so let's see. So here's there was somebody who asked me a question about one of the problems on the homework. It seems it was not that clear. So let me just restate it for you in case more of you have the same problem. So I think it was question 2, part C. So this was the true-false question about stable marriage, and what it said was, okay, so here's what the question actually says, and let me just explain to you so you at least know what it's talking about. So, you know, let's say that you're given an instance of the problem. What does it mean, an instance of the problem? It's just an input to the problem. So you're given, you know, A, B, C, D, you know, 1, 2, 3, 4. You're given their preference list, so each one has their preference list. And now you know that there's always a stable matching. We proved it, right? There can be more than one. But now this question says, suppose somebody is careless and they didn't create a stable matching, right? Suppose they just matched up A to 1, B to 2, C to 3, D to 4. We want to know how bad could things be? Okay, how much havoc could they have created in this process? So what this question asks you is it possible that you could, you know, for any n, no matter how large n was, that this could be a real disaster? Okay, that is it true that there's some instance, some way of setting up these preference lists so that and some way of setting up that matching, right? In such a careless way that if you look at any pair who have not been matched in this matching, they form a rogue couple. Okay, that it doesn't matter. You just pick any pair. You know, you just name them at random. You just say, well, how about C and 2? They prefer each other to who they are matched with. As well, how about A and 4? They too prefer each other to who they are matched with. Okay, so every pair who are not matched form a rogue couple. So this is a true disaster. And so the question is asking you, could you have a true disaster for every n? Okay, is there some way of setting up the preference list so that, and some way of setting up the pairing so that it's a total disaster? Okay? Okay, so back to what we were doing, which is the RSA crypto system. Okay, so I told you that you know, the RSA crypto system was invented back in 1977, and then what happened? Well, what happened after that was there was a great deal of excitement in cryptography circles, and you know, so the theoreticians, you know, in theoretical circles, it caused a great deal of excitement, and a lot of research happened, and then nothing much happened in practice, right? So a decade went by, nothing happened. 2 decades went by, nothing happened. RSA, one of them sort of enterprisingly tried implementing it. They tried doing it on a chip. Nobody really paid much attention. And then, well, 2 decades, maybe sometime in the 90s, it suddenly took off. Okay, why did it take off? Well, first because the implementations got fast enough, computers got fast enough, and secondly because they created a company called RSA. Okay, so in cryptography speak, you always talk about these two players, Alice and Bob, who are always, they're trying to collaborate, they try to communicate with each other. That's how cryptographers always speak. And they also speak about Eve, who is that person up there with the scissors, who's the eavesdropper, who's always trying to sabotage the protocols. Okay, so this is how the cryptography setup looks. You have Alice, who is trying to send a message to Bob. Meanwhile, Eve is trying to listen in on the line. Okay, so now what was so great about what RSA did? Well, RSA is what's called a public key crypto system. So what does this mean? It means that Bob puts on his website for everybody to see his public key. So he broadcasts N and E, which is his public key. So this is his public key. Okay? Everybody knows this. Okay, so everybody knows if you want to send a message to Bob, and your message is X, you take X raised to the power of E mod N. Okay? Now, the question is, at this point, Eve knows as much as Bob does. I mean, she knows what N is, she knows what E is. Why is she unable to intercept the message? And the answer is, in an information theoretic sense, Eve has all the information that Bob does. She just doesn't have it efficiently accessible to her. Right? Once she knows N, she could factor it and figure out P minus 1, Q minus, she could figure out P times P and Q, the prime factors. She could compute P minus 1 times Q minus 1, and then she could compute E inverse mod P minus 1 times Q minus 1. She could do all this, right? The only thing is, she can't do it quickly. And because she can't do it quickly, she just doesn't have a hope of figuring out what what message Alice sent to Bob. Okay? So this whole idea of a public key crypto system, before people thought about how to think computationally in this way, about what's easy, what's hard, this was just completely impossible to even dream of. And so, who dreamed of it? It was there was a pair of mathematicians, Diffie and Hellman, who dreamt of this in the early 70s, and then RSA, that's RSA. Okay, so they dreamt this up in the mid-70s. Actually, this is not what they looked like back then. People in the 70s looked like this. Okay? Okay, so well, that's Rivest, that's Shamir, that's Edelman. Okay, and so how did they develop RSA? Well, they were trying their best to, they came across Diffie-Hellman's paper. They were really excited about it. They were trying to develop a crypto system, and so the way they developed it is R and S kept coming up with schemes, and A kept breaking them. And so they kept doing this, and then they came up with a scheme that A could not break. And so they published it. Yes? Oh, yeah. What does Bob have that Eve doesn't have? Yeah, sorry, I forgot to tell you. So then, there's this private key, which consists of what? Well, The private key just consists of D, which is E inverse mod P minus 1 times Q minus 1. Okay? This Bob keeps secret. He might even throw away P and Q at this point. But the point is that this private key, in an information theoretic sense, once you specify N and E, D is uniquely specified. So you could go through and you could laboriously try to factor in and figure out what D is. And that's all in principle accessible to Eve. But in any practical sense, it's totally inaccessible. And this is what makes the RSA crypto system work. So you might hear the phrase one-way function. Okay? You know, where if I give you P and Q, it's easy to multiply them and create N. But it's very hard to reverse this. Okay? And then there's another term that you might hear, which is you might hear it less often, but it's actually a very, it's maybe an even more useful term. It's called a trapdoor function. Okay, you start with this one-way function, PQ versus N, and now you create this trapdoor function, which is given X and E, you compute X to the E mod N. Sorry, so let's say you map X mod N to X to the E mod N, right? So this is a function that you can compute quickly, but it's hard to invert. It's given X to the E, it's hard to compute which X it came from, unless you happen to know the trapdoor. Okay, what's the trapdoor? It's the factors of N, or it's this D. And if you know the trapdoor, so if you happen to know D, then you can reverse it. You can go backwards. And so RSA relies on this trapdoor function. The RSA function is a trapdoor function. It gives you a way of quickly computing X to the E mod N, so going from left to right. But nobody can go from right to left unless they know the secret. Once you know the secret, that's the trapdoor information, and that allows you to go backwards. And so Bob very cleverly picks the trapdoor first. And then he says, here's how you compute. Now everybody can compute, but only Bob can invert. Yeah? Now, the fact that this is public key is extremely important, right? So, this whole notion of internet commerce, right, where you're going to send your credit card number to a company without ever meeting up with that company in private and saying, actually, when you want to talk to me, use this secret information to communicate with me, right? That's what cryptography looked like before public key encryption, public key crypto systems. That would have been totally inadequate for internet commerce, right? Where you have millions of people who are trying to communicate with a central entity, right? Without knowing it personally. And so, this setting where that company just puts on its web page its public key, right? And then you can communicate with it, and nobody else can listen in. Right? That's exactly what's done here. In practice, what happens is when you communicate with Amazon, you do an initial session, which is using RSA, where you actually exchange a private key. You use RSA to exchange a private key, and then you use the private key to communicate with them. Okay, but you need this initial step to somehow, do something so that you can communicate privately, even though you haven't ever met before. And that's what public key crypto system allows you to do. Okay, so let's see. Okay, so how are you doing in terms of being able to focus? Do you want a minute break? No, really? Okay. Okay, okay, but you know, but to answer this question, you really have to focus. So are you fresh enough to focus? Yeah? I'm sorry? 1 minute. Okay, let's take 1 minute. Yeah.
So they use RSA to transfer that, like D, pretty much, but then.
Sorry, not to transfer D.
Oh no.
No. Sorry, it's to create a private. Oh, sorry. Maybe I should read. There are these symmetrical key crypto systems where Alice and Bob actually share a secret. So what you do is you set up some symmetric key, and then which is more efficient. Yeah. Sorry, I'll clarify now. Okay, so I said something which was a bit, it was easy to misunderstand. So let me just say it again. So what I said is, when you actually communicate with Amazon, your initial communication sets up a private key crypto system. So that's not the same as this private key, right? So it turns out that there are two kinds of crypto systems. There are the public key ones, and then there are the private key ones, which are also called symmetrical crypto systems, where Alice and Bob meet in advance, and they pick out a key that only they know, and nobody else does. So it's the same key that both of them know, right? Once you have that, then you can actually do this kind of communication even more efficiently than with public key crypto systems. But the problem is, to set up this common key, Alice and Bob have to meet in advance. So now instead, with a public key crypto system, what they can do is they can use this public key crypto system to set up a common key for themselves, a shared key, a shared random key. And then they use that in their symmetric private key crypto system, which is faster to actually carry out the rest of the session. Okay, so that's what I was referring to. Yes? Why do they need a common key? Well, I mean, they could use this public key crypto system, right? It's just that it's less efficient than the best private key crypto systems. So instead, what they use is they use the public key crypto system to initially set up their private key for the session, and then once they have the private key, they can use this faster communication method. Yeah? Yes?
So if Eve catches the private key,
then everything is lost.
okay, so it's dependent on the fact that Eve will never catch that private key.
Yeah, because the public key crypto system was secure. So they use RSA to communicate that private key, and then which is different from D. It's just some random number that they pick. They communicate it. They say, well, for this session, use this key, and use this symmetric crypto system. Right? Okay, that's what they do. Okay, so now, so far what I described to you is what the RSA crypto system looks like. Now let's try to see why it works. Okay, so to understand why it works, we have to understand some of the properties of modular arithmetic. Okay, so first, let's see, how do we know that x to the e mod n is a bijection. I claim the way we know that is because what we're going to show is that there's a decryption function which exactly decrypts, which means if you take x and encrypt it and then decrypt it, you get back x. Which means, how do you do, what does this mean? You take x, raise it to the e mod n, and now raise this to the d mod n, and you get back x. Now, remember one thing we said about reducing mod n, you can do it as many times as you like, or as few, you can either do it in the intermediate steps, or you can put it off all the way to the end. It's all the same thing. Remember we said this? So this is the same thing as x to the e whole raised to the power of d mod n, which is x to the e times d mod n. So what we're saying is x is the same as x to the e times d mod n. Okay. I claim that once you've proved this, you've actually established that RSA is a bijection. Okay? This is a general fact. So suppose I give you some function f, which maps a to b. A and b are finite sets. And suppose I tell you there exists G such that G of f of x is x for all x in A. I claim that this implies that f is 1 to 1. Does everyone believe this? Sorry. And I claim that if A and B are finite and f is 1 to 1, then this implies that f is also a bijection. Okay, so let's see that both of these things are true. First, we'll see that if there's an inverse, then f must be 1 to 1. And then if in addition, if it's on a finite domain, then it must be a bijection. Okay, so why is it 1 to 1? Well, it's easy, right? It's by picture. So here's A, here's B. Suppose by contradiction not. Suppose that f was not 1 to 1. So here's f such that, right? So suppose it maps x and y to the same image. Now how could that be? When we take x, we map it across and we apply g to it, we should get back x. Right? So g of f of x should be equal to x, and g of f of y should be equal to y. But f of x is f of y. So g of this is supposed to be that, but it's also supposed to be that. That's a contradiction. It can't be. So that's a contradiction. Right? So it must be 1 to 1. If it has an inverse, it's 1 to 1. Now how do we know that if it's 1 to 1, it's also got to be an onto? It's a bijection. So for that, we have to invoke what's called the pigeonhole principle. It's actually non-trivial to say that if it's 1 to 1, it's on a finite domain, it must be onto. So here's the argument. So we have a function f, goes from A to B. Let's say it's going from A to A, same number of elements. And it's 1 to 1. Okay. Okay. I claim that it must be onto. It must be the case that every element here is hit by something. That's what it means to be onto. So how do you prove it? You suppose not. Okay, you suppose that there's some element which was not hit. So now you have n elements here on the left, which are mapping to n minus 1 elements on the right. Yeah? And we are claiming that no two hit the same element. It's obvious that can't be, right? Except that The point is, we don't know how to say it without invoking an axiom. Okay? And this axiom is called the pigeonhole principle. It says, suppose you have n pigeons and only n minus 1 pigeonholes, then 2 of the pigeons must be sitting in the same pigeonhole. Okay? People have tried to prove this using the remaining axioms in mathematics, and they've never succeeded in doing that. It's independent. So this is a new, it's sort of a new axiom you have to invoke every so often. And it turns out this is one of the more difficult steps in a proof. So, well, that's what, okay, so we've proved it. So now okay, so now to show that the RSA function is a bijection, all we have to do is we have to show that x is the same as x to the e times d mod n. Okay, so how do we show this? Okay, so this, it turns out, is actually quite an interesting thing to show. So it relies on what's called Fermat's Little theorem. Okay, so unlike the last theorem, this one he actually had a proof of. Okay? So what it says is, if you have any prime p, and if you take any number between 0, which is any number mod p which is not 0, then a to the p minus 1 is congruent to 1 mod p. Okay, so for example, if you look at the number 11, and so you look at any number like 2 to the power of 10, it must be congruent to 1 mod 11. Okay. How do we see it? Well, okay, we could try computing it, but yeah, it's easy to see, right? So 2 to the 4 is what? 2 to the 4 is what? Is 5. So 2 to the 5 is what? Is minus 1. Very good. So 2 to the 10 is 1. Good. Okay. So 2 to the 10 is 1 mod 11. Okay, but how do we prove it? Okay, so it turns out, so the proof is incredibly clever. Okay, so here's how the proof goes. So the proof goes like this. So we want to show, okay, so let's do this for 4. We want to show that 4 to the 10 is congruent to 1 mod 11. Right? Any number mod 11. We want to show 4, so pick an arbitrary a. So how do we show 4 to the 10 is congruent to 1 mod 11? What we do is we first construct a bijection between the numbers. So we rule out 0, so we cross out 0. Okay, and so we can look at the, mod 11, so sorry. I shouldn't have included 11, should I? Okay, so we rule out 0, meaning we rule it out from both ends, and now, so we have the numbers 1 through 10. Now, let's look at a bijection. Let's map 1 to 4, 2 to, so let's map x to 4x mod 11. So 1 goes to 4, 2 goes to 8, 3 goes to 1, 4 goes to 5 goes to 9, 6 goes to 2, 7 goes to 6, is it? 8 goes to 10, 9 goes to 3, 10 goes to 7. Okay, so it's a bijection. How do we know it's a bijection? Could we have said before we started that it must be a bijection? How do we know? 4 and 11 are relatively prime. Why? Because 11 is a prime. Okay, so GCD of 4 and 11 is 1. And what does that tell you? that there's an inverse. Right? So 4 inverse exists. So if we call this function f, right, then there's a function g, which is g of y equal to y divided by 4. What's y divided by 4? We don't care, right, because it exists. Actually, y divided by 4 is 3 times y, right, because 3 is 4 inverse mod 11. Okay, so by the theorem we just proved, since there's an inverse, it's a bijection. Okay, but now, what does this have to do with proving 4 raised to the power of 10 is congruent to 1 mod 11? So this is where this incredibly clever argument comes in. Yes? Oh, what's 1 over 4? What's 4 inverse mod 11? Well, 3 times 4 is 12, which is 1 mod 11. So 4 inverse is 3 mod 11. Okay, so I was just doing it in my head, but yeah, okay. Okay, so, okay, but now, okay, how do we show that 4 to the 10 is congruent to 1 mod 11? So let's multiply out the numbers on the left. It's the numbers on the left multiply out to being 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Mod 11, right? What about the numbers on the right? Well, let's count them in a different order. It's 4 times. So 4 times 1. Okay, so let me write these in a different way. So let's say this is 1 times 4 times 2 times 4, right? Because I'm just counting them in this different order. It's 4, 8 times 3 times 4 times 4 times 4 times 10 times 4, right? So what do we get here? This is 1 times 2 times 3 times 4, 5, 6, 7, 8, 9, 10 times 4 to the 10. Okay? Yes? We're just counting in a different way, right? We're just saying you multiply everything on the left. It's the same as multiplying everything on the right because it's the same numbers. But then we said on the left it was 1 times 2 times up to 10. On the right we are choosing them in a different order, right? An order given by this function. So the first one was 4, which is 4 times 1. The second one was 8, which is 4 times 2. The third one was 1, which is 4 times 3. So each of them is 4 times something, right? So it's 4 times 1, 4 times 2, 4 times... Okay, so you simplify that. It's 1 times 2 times 3 up to 10 times 4 to the 10, because we got a factor of 4 for each one. Okay, so this is congruent to this. So you cancel these two, and you get 4 to the 10 is 1. Yes? Now, is that clever or what? This Fermat was really something. Okay, but wait, before we cancel these, what right did we have to cancel these? Why could we cancel them? I'm sorry? Yeah, remember, 11 was a prime, so we could cancel. Each of them has a multiplicative inverse. We can divide by, we can divide by 2, we can divide by 3, we can divide by 4. Why? Because each of them is relatively prime to 11. So we cancel not the whole thing, but we cancel one at a time. It's the same thing. We cancel the whole thing. Okay? Okay, so now let's do the final step. Okay, so what did we really want to show? We wanted to show that x to the dE is congruent to x mod n. Right? Remember our conditions? D was E inverse mod P minus 1 times Q minus 1. So what's x to the d times E? So d times E is congruent to 1 mod P minus 1 times Q minus 1, which means that d times E is 1 plus k times P minus 1 times Q minus 1. So we want to show that x to the 1 plus k times p minus 1 times q minus 1 minus x is divisible by n. Okay? So what if I showed you that p divides this and q divides this? Wouldn't you be convinced that n divides it? Right? To show you that n divides this, I must show you p divides it and q divides it. Okay, so let's see that p divides this number. Well, what's this number? It's x times, so x is common, and then you get x to the k times p minus 1 times q minus 1 minus 1. Right? Okay, so why does p divide x times this number? Is everyone following me? Why this is sufficient? Okay. So, well, there are two cases. Case 1, p divides x. In this case, I bet you can finish off the proof. Yes? Case 2, p does not divide x, which means that x mod p is either 1 or 2, right? So x mod p is between 0 and p minus 1. Right? So now Fermat's little theorem applies, which means that x to the p minus 1 is congruent to 1 mod p. So what's this? This is x to the p minus 1 whole raised to the power of k times q minus 1, which is 1 mod p. Right? So this was 1 mod p. And when you raise it to anything else, it stays 1 mod p. When you subtract off 1, you get 0 mod p, which means it's divisible by p. Right? That's it. So that's why RSA works.